It looks like yes.
Fine. Good afternoon, everyone. Welcome to another Safari Live seminar. Today, we are really happy and honored to have with us Christian Pilato. He's an assistant professor in the University Politecnico di Milano. Today, he's going to present with us his work and ongoing research on modern trends in accelerator design with high-level synthesis. Thank you. So the floor is yours.
Thank you. Thanks so much. So sorry for all the troubles with the connection. So I hope that now we are all set. So thank you for hosting me. Thank you for you to be here. So I will start with like a couple of words about me. So I'm an assistant professor at the Politecnico di Milano. I got my PhD at Politecnico. I stayed there a couple of years, and now I'm an assistant professor there. But in the middle, I took a little bit of a detour. I stayed 3 years in the US at Columbia University, and then I came back to Europe for a couple of years in Switzerland. So not in ADDH, but just was in Lugano. So then I spent few visits here and there, and at the end I was managing, or at least I was working in a few research projects, starting from the FP6 to the H2020, and now I'm also working on the H2020 project that I'll talk a little bit in a second. So first, I would like to start a bit about the fact that we all know that we are in the era of big data. So what does it mean to be in the era of big data? So basically, it means that we have applications where, in general, we can combine, or we can consider that we have intense computational intense kernels that we may want to accelerate to process the vast amount of data that we need to manage, and we have heterogeneous data sources. So we have data sources that could come from different sources, and could be historical data, could be real-time data. We need to assimilate them, and we need to get knowledge out of it. I will make 3 examples out of the ones that you may consider. The first one is an application on renewable energy production prediction, where you want to improve the quality of the prediction of the energy production, especially wind production, by combining weather models with information about the plants. So in this way, you have the data from the weather model and the information about the plant, and based on that, you improve the prediction. The second one is an application to monitor the quality of the air around industrial sites. So you still use weather models, but in this case, you have a completely different use of this data. So you have the same data, but a completely different use. What is the use in this case? Is that you want to combine with the action that you can do in the industrial site, for example, based on the weather condition, to activate or deactivate some mechanism to control the emission of particles. Right? These solutions are expensive, and for example, they are not needed if there are certain air conditions. So you already see that in this case, you have 2 different applications that are both based on the same base concept, that is the creation or weather prediction models, okay, so scientific applications, that you and then once you create these models, you can use the data that are coming from this model, combining with other models, so heterogeneous data sources, to improve your system. So this is already an example where you can combine the same computation with different sources. Then the third case is when you want to model the traffic inside the city. In this case, you have a completely different characteristic of the computation. It's more irregular. It's more based on the actual cases that you have inside the city, and you want to improve the overall performance. So you can already imagine that once you have a lot of data and you have to extract knowledge and make decisions on top of them, you may want to use machine learning algorithms. So that's already another kind of computation that is quite popular in big data applications. So what are the challenges and trends for creating accelerators in this case? First of all, as we said, we have big data application with heterogeneous data sources. Once you have these applications and you have this vast amount of data, one particular type of architecture that you may imagine to use is architecture based on FPGAs. FPGA are very good when you have the possibility of exploiting spatial parallelism, and you may use these architectures to create accelerators for specific kernels. What are the problems? The problems, there are several problems in this case. The first of all is that application designers are not FPGA experts, are not even able to create an accelerator, or they are not even able to understand what you are talking about. There is this say funny story, it's not so funny when it happened, that we were talking about, we were starting writing the proposal, okay, for the project that we are working on. And we were talking about with the people working on these weather prediction models. And we were discussing with them to understand what was the best architecture, FPGA architecture, to execute these applications. And I have to admit that maybe I posed the question in the wrong way, and I said, do you want cache coherence? Imagine what was the answer. What was the answer?
What's cache?
Huh?
What's cache?
It's even worse. They said, is this something to eat? Okay? Because they don't even know what we were talking about. And we said, okay, this is gonna be fun. Okay? This project is gonna be fun. And it is fun in some way. Not always, but it's fun. Okay? Because they don't know what we are talking about. And this means that they need us, right? If they want to use FPGA. Because they said, oh, we know that FPGA could be good for our application. Can you help us to do that? Okay, so now we have to design accelerators. We all know that designing hardware accelerator is not simple because of many reasons. It's not something that you can just do by running a tool, taking the result, and that's it. You have many optimizations to be done. You have many characteristics that you have to take into account, the application, the architecture, and so on. And every time you change, for example, even just the FPGA, you may have a completely different architecture based on what you want to achieve. Okay? So how can we design and also use accelerators for these kind of applications? So we divide the problem in at least in three main goals. The first is we want to increase designers' productivity. We don't want to spend months to design an accelerator for an application because, we are accelerating the application, but if the application is 3 times faster, but then we spend 1 month to design the accelerator, we lose any reason to do that. Obviously, we want to improve the quality of the accelerators, okay, or at least match what the designer could do by hand, right? Then we want to increase the security maybe of the hardware and the data, right? So we are using applications that manage, in some cases, sensitive data, right? And we don't want to have any leak. So we divide the problem at what we can do at design time and what we can do at runtime. At design time, it's important to increase the designer productivity, that you don't create a different flow for any possible, for example, input that you have. For example, if you use a domain-specific language, if you use C++, or if you use a machine learning framework, that is in most of the cases nowadays in Python, you don't want a different flow for each of them, because otherwise you have to design every possible combination. And we already know from, I don't know, compilers, that is almost impossible to be done. But then you may have nodes with different characteristics. So an idea that you may have is the creation of variants. The variance is an alternative of your design that can exploit different characteristics. Maybe can have more bandwidth with the memory, because you may have a node with a different bandwidth. Or you may have a larger FPGA, so you may use more resources. Or you may have more smaller nodes, and so you may want to use them more efficiently. But if you create the variance, then you need something at runtime that matches these variants or these alternatives that you may have with the actual characteristics of the node. So, for example, you get a node that you can use, and based on the characteristic of the node that you can use, then you have to understand how to select the appropriate variants for the execution. Then, in any case, whatever variants you select, you have to perform efficient data transfers. Otherwise, you spend more time in transferring the data than doing the computation. And then, whatever you want to do, you may need to introduce monitors inside your system to monitor the power, to monitor the stalls of the data transfers, or even just to monitor possible intrusions. So, in this context, I will explain now in a few minutes, is this Everest project that we are in which we are working on, and this is an European H2020 project that started more than 2 years ago, and it will last another year and a half. And it's a project with 10 partners. IBM here in Zurich is the project coordinator, and I'm in charge of the scientific coordination. The idea is indeed that we have big data application with the data sources. We have 3 use cases. Guess what we have seen before as examples. And we want to understand how to map them to FPGA-based architectures. So we have a CPU-based infrastructure, right? So a supercomputing center in Czech Republic, where we try to offload then the computation to 2 FPGA-based clusters that are based here in Zurich, based on 2 different types of FPGA. We will see the details in a second. The idea in this case is to do this matching. We are developing what we call the DRS SDK. That SDK stands in our case for System Development Kit, because what we are doing is we are trying to design the complete system that will go into the complete infrastructure, CPU plus FPGA. So in this case, the SDK, the final goal is to have interoperable tools. So with the idea that possibly we could change the HLS tool that we want to use, or we want to change the nodes that we want to use, where we can match the target system, the application workflow, and the data characteristics. So we can also extract characteristics from the data and optimize them. So at compilation, we try to unify the hardware generation flow based on the concept of MLIR, that is this extensible high-level representation that can be used to support multiple input flows. And then we combine high-level synthesis and specialized memory architectures to design the hardware part. And then at runtime, we do the automatic allocation of the target nodes and the virtual machine on top of them, so that we can expose hardware resources. And once we expose hardware resources, we can use an auto-tuning framework that is exactly the part that can select the variants and can change how the code is executed based on what we are running. So a couple of words about the system. So the CPU reference system can execute end-to-end workflows. That's already in production for executing large applications. Can already manage storage and data transfer across the nodes. So this is something that we don't have to care about. And we extended, they extended the ones that are working in the data center, or we as Everest, with the support to offload tasks to the FPGA servers. So we identify the task, we identify the type of resources that are needed, and once these tasks are offloaded, we can allocate the corresponding nodes. And the nodes could be based on two different types of nodes. One is a system that is developed by IBM. Is a system where they call them disaggregated FPGAs, where you have multiple FPGAs in a cluster that are directly attached to the network. In this case, there are small instances. The data are fed into the system through the network with a kind of high bandwidth. And so they already have a framework to support the interfacing between the network and the system, so that you can focus on the generation of the computational part. Similarly, we have a cluster with PCIe attached FPGA, okay, Xilinx Alveo FPGAs, where you can do more high performance computing workload. In this case, we have the possibility of using frameworks to target that, and so we can raise the abstraction level to create the nodes. Okay? What has the advantages is that you have spatial parallelism. You have a lot of FPGA resources where you can offload, or you can implement the computation. You have high memory bandwidth, or in any case, high bandwidth to provide the data, either for the Alveo clusters or even through the network. You can have a high bandwidth to process the data, but also you have different nodes to better match the application characteristics. Maybe you have some small computation and you can just distribute them across the cloud FPGA nodes, or you may have large HPC computation that you prefer to be on the FPGA Alveo cards. Okay, this is something that is an advantage, but it's also something that you need to support with proper tools. So you may have data-intensive memory-bound applications, so you have to understand how to deal with this memory. You have limited FPGA resources, especially for the memory resources, and again, you have to understand how to use them better. So in this analysis, I think we can identify three main gaps. Okay, the first gap is about the input language and the input framework that you may want to use in your system. So here we identify a gap between the application designers and the hardware software designers. And the application designers are, as I said before, people that are completely unaware of any hardware details, okay, any architectural details. They could be physics, they could be mathematicians, okay, and they know very well their application, okay? All their details, but they don't know how to use the target platform. Okay, so maybe they want to use framework that are not currently supported by the tools that you want to use for the FPGA. How to talk with them? Okay? So how we can solve this communication problem. The second is about the optimization of the accelerators. Okay, so now that we understand the functionality that we want to implement, we have to create the accelerators. And still you have a gap, for example, between the compiler experts that are the ones that may need to digest the code that is being provided, and the hardware designers. Okay, we have another experience when we were optimizing some code where the compiler expert said, oh, I found this little very interesting optimization for the compiler where you can do this and that. And we said, that's totally fantastic if you execute on CPU. But if you execute that on FPGA, you break all the guidelines that you may have for acceleration, for pipelining the loops, and so on. Okay, so you need again to understand which optimizations and how to apply optimizations to be used in way to create efficient hardware. Okay, so we want in this case to create compilation flows that are hardware oriented and maybe also data driven. So based on the characteristics of the data that you may have. Then now we have the accelerators. Okay, so now we design a very nice piece of Verilog or VHDL, but we still need to put them into a system. In this case, is the hardware designer that have to talk, the designers that have to talk with the system designers. Maybe with, in this case, you have to talk with the IBM guys that are providing cloud FPGA to connect your accelerator to the system. Or you have to deal with the Xilinx tools for connecting to the HBM and so on. Right? Because otherwise you're creating very good accelerators, but they are not able to process the data because they are still waiting for the data. So in this case, we want to understand how to co-optimize the kernel and the entire system. So first, let's talk about how to translate from software to hardware. So high-level synthesis is a very nice technology that allows you to translate a high-level specification into synthesizable hardware. So the first question is how to design, how to write your high-level specification. Because one important aspect is that you have many different ways to write your code. Okay? You may want to do code transformation from one point to another. Okay? And then you may use from each of these, you can generate high-level synthesis and generate a set of Pareto, a set of alternative design. Then if you build the complete Pareto of your design, so the complete trade-offs of your design, what you see is that maybe to go from one point to the other, so to one extreme to the other, you cannot do that simply using HLS. You have first to change the code and then to reapply other optimizations. So what happens is that the input code and how the code is written is extremely important. And for example, the C doesn't express concurrency, we know that. And you maybe want to fake it, or you want to understand how the tool behaves to help it to extract concurrency. Then pointers is something that is extremely nice to be used in C, but not in HLS. Or also multi-port interfaces is something that is difficult to be expressed in C. Okay? So another So one important observation is that C, that is considered high-level language, maybe from hardware designers, is still a low-level language for hardware design. Whatever you can think about. Because if you imagine, once you write C code and you want to synthesize that C code, you are already implementing some decisions, especially for the memory. For example, you decided a certain memory layout for the arrays and a certain way in your code to scan the elements and to access the elements. Okay? At that point, you're already making decisions and you have to live with them when you design the hardware. If you want to design a different hardware, maybe accessing the data in a different way, maybe you have to modify the code. And if you want to do that manually, you need to know what you are doing. So it means that you have to be an FPGA expert. Okay? So what to use as an input language for system specification is still an open question. Okay? So once we want to identify possible challenges that we may have for high-level synthesis, here on the left you see a classic HLS flow. Is a picture that is being intentionally taken from a popular HLS flow, maybe one of the most popular for FPGA, that is the Xilinx Vitis HLS. So you have C++. Okay, so if you want something that explores your code at a higher level, you need something that is on top of that, explores your code, and then generates C++ to be then synthesized by this. Right? And then you have a front end that is used to generate the representation, and then you have the low-level part that does the real FPGA synthesis. So optimization, lowering, and then you have the scheduling, and so on to generate the final RTL. So we can have what the initial part is the compiler front end. Okay? And here we can imagine that you have a problem of a challenge of programmability. So you have to understand the interaction between hardware and software. You have the actual HLS engine that in this case, you want to understand how to do the optimization and how to want to generate an efficient architecture. And then you have the final backend where you may want to, for example, to understand how to protect the efforts that you have done. So something that I hope that at a certain point I will stop to say that, but still I cannot stop, is that high-level synthesis at the moment cannot replace a human design. Right? It's something that automates the generation of the hardware, but the decisions still have to be done by a human. Right? And as long as we don't remove this barrier, we will need someone that drives the high-level synthesis. Also, design space exploration tools still need a designer that, for example, once you design a Pareto, decides what is the best design for your system. Okay. So I'll make an example that is similar to the application that we have to face in the project, and is an application for computational fluid dynamics. Okay? It's a numerical simulation application that can be solved by computing a set of small contribution on independent data. So it's an extremely massively parallel architecture where you have to apply this operator that is called the inverse Helmholtz operator to each of the data blocks. Okay? So this operator is composed of 3 tensor operators that are repeated millions of times. They are parametric with respect to the degree of the polynomial to be approximated, and this parameter P. On the right, you can find the DSL, domain-specific language description of this operator, where the P, so the degree, is equal to 11. So you see that the first 6 lines are the declaration of the input, output, or intermediate values, and the degree, so the dimension of the tensor, and then the three operators. Okay, you see that it is a completely high-level description. There is no description on how to operate on the data. There is no description of how the data are laid out in memory. Okay, this is good for an application designer because he or she doesn't have to know all the details. So then the job now is all on the compiler. Now here you see a decomposition of these three operators. So the T, R, and B here are decomposed, and you see they can be translated into basically 7 measure loops, okay, multi-level loops. So every time you have these characteristics, you see that you have temporary values from one loop to another. And also you have special characteristics, like, for example, S is reused in all the loops, while D is used only starting from the second operation. Here you see also when P is equal to 11, you see a characterization of the amount of data that you need for each single element. Okay, so you need less than 100 kilobyte of data per kernel. Okay? So seems not much, but if you have to repeat that millions of times, you see to end up to gigabytes of data to be processed. Okay, then you have some more issues. You may have some application-specific optimizations that the designer knows very well, and the hardware designer doesn't know. Okay, so here you can I can tell you another something that happened again when we were designing this accelerator, because okay, if you look at this, after we designed the picture, we realized, oh, but X is the same that is used in all the kernels. So after a while, we realized, oh, but S is constant. And the application designer said, oh, yes, we forgot to tell you that. Okay. And we said, okay, now we have to deal with that. So we have to understand how to make it constant across the computation. Okay. So spoiler, we realized that it is more efficient to send it all the time rather than reusing that on FPGA. Right? So that was something that we discovered. But then when they said that, we said, oh, we also forgot to tell you another thing. D is diagonal. So all the other elements in the matrix are 0. So you don't need to compute them. Okay? So this is something that they know. Okay? But in some cases, it's difficult to be expressed in the code. Okay, so you have to understand how to use them also during the design. For example, how to make it as constant or not. Then you have limited VRAM resources. So 100 kilobytes in the CPU world seems to be nothing. In FPGA, it's already something. Okay, so you need to understand, for example, if you want to put many kernels in parallel, if this can become a bottleneck. Okay, then, and we want to optimize the local storage. Then we have system level optimization. So we want to create batch of elements to execute this computation, and we want to understand how to trade off communication and computation. Okay? In a way that we also hide communication latency. Yes.
What's the biggest design tool for these application designers?
Performance.
Performance.
Yes.
They don't care about energy or this.
At the moment, the goal was to, at least in the initial experiment, to extract the maximum parallelism and to achieve the best performance. We wanted to at least to beat the CPU performance, at least to see if it was possible, okay? Because that was initially the idea also for application design. Application designers don't care about energy, okay? The energy is from the system providers because they are the ones that have to pay the bill. Okay? Then they will charge it to the application designers at the end. Okay? But initially, those are the ones that have to pay for that.
But are they trying like GPUs as well, or they're running everything on CPUs?
They also tried GPUs, and they had a mixed feeling. Right? So in some cases, they were able to, again, you know, that writing code for GPU requires, again, some rewriting and so on. So they had, okay, we had some good results from a GPU. We wanted to see if what is FPGA, right? And now, as technology providers, and they were in the middle between the application design and the system design and the platform providers, we also wanted them exactly to bring the problem of energy efficiency. We say, oh yes, you may achieve the same performance of GPUs or even better. Let's see also the power consumption. Okay. Okay, so these are more or less the all the challenges that that we had. So what we can say, we can for these challenges, we can identify three trends in high-level synthesis. First is this automatic translation from DSL, or at least from high-level languages, especially by using MLIR to support multiple input flows, and to combine that with high-level synthesis to generate the hardware, whatever it means to generate high-level synthesis. Then for system level optimization, we want especially to focus on the customization optimization of the memory, okay? Especially with system level architectures and specialized memory systems for both on-chip and on-chip memory and data transfers. And then for hardware security, we want to explore how to use in case logic locking and eFPGA reduction to protect the intellectual property. So to talk about DSLL to bitstream, our focus was indeed to optimize the memory. So we started from the description. The CFD length description is the description of the operator that we have seen before, and from there we generated code, and the compiler, you see that we have optimization level, compiler level optimization, where you can create alternative C code with different, for example, memory layout and so on. And doing HLS, you can extract information about the resource, the latency, and so on, to understand, for example, how many of them you can put in parallel and so on. But then the idea is to decouple the generation of the memory from the kernel HLS. So for example, the kernel was synthesized in a way in which even all the local memories were exported, so we could perform more optimizations. And then we put everything together to do the optimization and to generate the complete system to go on FPGA. So our focus was to optimize the local memory and the complete system. So in one case, we do the optimization of the private local memory, so the local storage. And in the other case, we focus more on the data movement for the system architecture. So for optimizing the private local memory, we use maybe the most the simplest concept that you may imagine. Right? So we wanted to reuse data structures where they were not used, okay, anymore, and to reuse them across multiple arrays, multiple data structures, okay? With a very simple definition. So two data structures are compatible if they can be allocated, so they can be instantiated or placed in memory into the same physical memory IPs. And you may have two conditions, at least, that we identify in this law. First, you have a complete address space compatibility. So you can put the two data structures in the same address space, so in the same memory space, because the two arrays are never alive at the same time. So you can reuse that memory space. So maybe this is something that you don't care in software. So if you have a 11 by 11 by 11 array, so it's an array with 1,000 elements, it's not that much. Even if you allocate two of them, it's okay. In hardware, it means that you can save half of the space. Memory interface compatibility is something where the ports could be reused. Why? Because, for example, you never do the same operation at the same operation at the same time. So you never read the two data structure, or you never write the two data structure at the same time. So imagine a dual port. If you write in one and you read from the other, you can use the two ports in parallel. Okay. So this is interesting because this information can be automatically extracted during the compilation flow, and you can build a graph like that. That is exactly the graph that describes the compatibility of the operator that we have seen before. What is this graph? This graph is what is called memory compatibility graph. It is a graph to describe this sharing opportunity among the data structures. So each node represents a data structure to be allocated in memory with information about the size, the number of elements that you need, and each edge represents a compatibility that you may have among the data structures. So you have, for example, these two compatibilities. Here you see a possible example among three data structures. Okay, so A0 and B0 are address space compatible, and A1 and B0 are have the same type of compatibility. So once you have this type of compatibility graph, you can define a click, and the click is a subset of vertices that is completely connected and represents data structures that can share the same memory piece. Because if it is a click, it means that each node is compatible with each other. Okay, so everyone is compatible with the other. But now, if you analyze that graph, you may ask what is the best solution. Okay, and the best solution, I mean, you may have at least, you can put A0 and B0 into the same click, okay, and A1 into another, because obviously you have to partition that graph into clicks, or A1 in B0 and A0 in the other. Okay, which one is the best? Okay. Which one is the best? As a good engineers, I always say to my students that the correct answer most of the time is it depends. Okay, it depends on what? On the characterization that you do for each of the click. Okay, so what we do, we enumerate all the clicks, so we identify all the possible clicks. We give a characterization, so we give a cost to each of them. For example, in terms of memory IP that are needed to implement that specific click. Okay, and then we do a memory cost minimization, trying to find a partition of this click that minimizes the cost. Okay, for the click characterization, we generate the corresponding implementation, and we do a quick evaluation of its cost. And once we have all the cost, we can have an IP formulation to extract the correct and exact solution. So for this PLM controller, is something that you can generate very easily, because once you have the configuration of the blocks, the data structure, and so on, you can generate the corresponding logic. It's something similar to the concept of accessing block cache blocks, where you can partition your address that is coming from the processor, from in the case of the cache from the processor, in this case to the accelerator, to identify first which is the block that you target inside your click, and then the specific offset inside it. Okay, and this becomes extremely efficient, like in caches, when the size is the number of the blocks, the number of the ports is a power of 2. And in this case, you can also support multiple ports, accesses with multiple ports. Okay, so once we evaluated these on our Helmholtz trend, you see here some data. Okay? Obviously, the amount of resources is pretty much the same. Okay, once you go from using the sharing and not using the sharing, at least in terms of loads, you see the first line here, second, and so on. But then what is important? The important part is that if you don't use the sharing, you cannot fit 16 kernels inside your FPGA, simply because you don't have enough VRAMs. The number of VRAMs is around 300 and something in the FPGA that we used, and using 16 kernels required almost 500. But if you use sharing, like the compatibility graph on this, like the cost minimization on this graph, okay, we were able to achieve a situation where 16 kernel can fit into the FPGA, while still the amount of resources is extremely reasonable. The LUTs are still around 33%. So it's still a design that is feasible. And indeed, you see that without sharing, you are limited to 8 accelerators. Okay, so you have a speed up around 8x. Okay? Actually, the total, including data transfer and so on, is around 7x. But if you can put 16 kernels, you go to more than 12x. Okay? So you can have a speed up because you better use the memory resources. Okay, so you better exploit the parallelism. So now you have to go at the system level. So at the system level, you want to put all your system together, and you want to put your accelerator that you may you generate as a sort of black box. So since you have the possibility of using the black box means that you could use C code that is synthesized from C from Vitis, or you can use directly an RTL block that, under certain assumption, you can plug it and pray that it works. Okay, so you can replace it with different tools, and you can generate the memory system around it. Okay, so the idea is, since we want to focus on the optimization, we generate synthesizable C++ code so that we can use higher synthesis and all the science by these tools to generate then the complete system. In this way, we simply need platform-specific description, for example, to understand which type of hardware, which type of elements we have. We have platform libraries because we may need to know how to send the data from the host and so on, especially because then we will need to take care about the hardware-software interaction. So the optimizations that we integrated are pretty standard, say for computer architecture. So double buffering, or in general ring buffering, to hide the latency of the communication between the host and the FPGA. And especially in this case, we do automatic batch sizing. So we determine how many elements we can send so that the communication time is balanced with the computation time. And also the amount of elements that you send fit into the memory space that you can transfer to the FPGA. The next is to use efficiently the bus, because, for example, in some architecture, you can have large buses, like 256 bits, and you may need to use them efficiently. I have to ensure that using those 256 elements efficiently is not so easy, okay? Because you have to extract data, you have to pack data, and so on. Okay? And once you need to understand this, you also need to understand how to lay out the data on the bus or on the memory to transfer them efficiently, because then you don't want that the packing, unpacking, or accesses to the memory becomes the bottleneck. And then the last one is the data flow execution, where we want to enable kernel pipelining almost in an automatic way. In this case, we want to automate pre-HLS code transformation together with the compiler. So our system generation flow starts from the characteristic of the parallelism of the algorithm, okay, information about that, the characteristic of the target platform, and the interfaces of the modules, because we need to understand how to interface, how to send data to these elements. And what we produce is the synthesizable C and C++ code of everything that is around the kernel. So the CO, so all the elements to feed the data in, all the functions to read the data from the memory of the FPGA, in our case, the HBM channels, but also on the outside, how to prepare the data, because maybe some transformations require, especially in the layout of the bus, auto modification, how the data are sent to the FPGA. Okay, so the idea is that we want to create parallel computing unit as much as they can fit. Yes.
But can it create like some sort of memory hierarchy as well?
Yes, that's the ultimate goal of the next 1.5 years. Okay. So the idea, or at least as long as Stephanie will stay with us in terms of PhD. Okay. Because indeed, our work in this project is exactly to customize as much as possible this memory hierarchy. So, for example, to have prefetchers, to have configurable caches, or specialized caches, and so on. Yes.
And also, I saw you was using a double data type. Was
Yes.
there some reason for that?
Because to use doubles.
Yeah.
Because the application designers said, "Oh, we want full precision, so double is the maximum that we want."
Not flow, like single.
I'll show you then some results for that. But this is something that we are able to manage, but it's not up to us to decide what is the precision that you want in the application. Especially in this application, the use of the precision is extremely important because you have a problem of numerical stability. Okay, so they want, in their opinion, they wanted to have a precision even more than double. Okay, because I mean they don't pay for that, so who cares in their viewpoint? But you know that having that in hardware is extremely expensive. Okay, so this is indeed the process to, for example, to have custom floating point representations, or even fixed point, and so on. So from the architectural viewpoint, for us is not a problem, because I mean the problem of the data type is mostly inside the kernel.
Yeah.
Okay. Around is you just need the number of bits that you need to transfer. Okay. So from our viewpoint, we can use whatever you want. Okay, then it's a problem of the kernel how to use that.
I was just thinking you can have like more resources, right? If you know.
Yeah, and then you inside of these you can have a memory hierarchy, but you can also have some more intelligent policies to coordinate data transfer or even to protect data transfers. So you may have data that are encrypted and so on. So to go on the results, and now you see that what exactly what we were discussing about. So here you see on this 16 red dash line was the CPU implementation that was our target. So obviously the baseline, as always, the initial hardware design is slower than your target, but as you progressively increase your optimization, or you introduce optimization, you reach a 44 gigaflops. That is actually 6 times fast. Three times, almost 3 times faster, 2 point something faster than your baseline. Okay? Here you see something interesting, that if your bus optimization is not done efficiently, okay, and you are aiming to use the 256 bits, instead of speeding up your computation, you are slowing down, because you go from 3x down to less than 1. From 3 gigaflops to less than 1 gigaflops. Okay? But then if you do the bus optimization better, then you really achieve any goal. But then if you also change the data type, obviously you can put more kernels, or actually the logic is faster or simpler, and you can go, for example, up to more than 100 gigaops. Okay, so you say that at the end, our final result is more than 100 times faster than the initial design. Okay. And also, they are 6 times better than the implementation on the CPU. Okay. Here you see some projection about the efficiency, gigaflops per watt, and you see that is even much more efficient than CPU. So here you see really a graph that motivates people, at least those application designers, to use this type of architecture, because this was an efficiency they were not able to achieve, not even with GPUs. Okay? And you see also something interesting, because here we also have different precision degrees. So sometimes you say, oh, I may want to reduce the precision of my degree, because if I reduce the precision, I use less data. But that doesn't necessarily mean that you are going much faster. And also you use more CUs, and at a certain point, instead, you see a very efficient design, okay, that you may imagine it is very efficient because it's fixed point, 32-bit, a lower polynomial degree, many CPUs, and then you see that the silence completely messed up the design, and the efficiency was much lower, even comparable to the CPU, because the design was completely messed up. Okay? So this is something, again, that you have to consider. And then you can configure exactly these custom data formats that we were talking about. So once you do that. So now you spent a lot of money to optimize your accelerators. Not even just for FPGA, but in general. Okay? So you spend a lot of time, a lot of nights, a lot of money also for testing. Okay? You may want to design your chip, but you know that your architecture is more and more composed on multiple IPs, even coming from different vendors. Okay? At this point, what you do is also to then give your design to be fabricated to an external foundry. Okay? And every time you give something to someone else, you cannot trust that person, okay? Because every time there could be malicious intentions. Okay, so what is possible is to reverse engineer the chip, duplicate that, and resell it on the market. Was found that for clothes, for shoes, why don't to do that for chips? Okay, they estimated that only in 2020, okay, the semiconductor companies estimated a loss of $4 billion due to counterfeited chips, and this is only what they knew. Okay, usually what is this is only the tip of the iceberg. So the idea in this case is that everything that you do at the netlist level, so once you deliver at the level that you deliver the chip to the foundry, you can do something that has little semantic information that can be protected, and also little impact. Okay? The classic example is a constant. If you want to hide a constant because you have proprietary coefficient in your algorithm, you cannot do that at the netlist level. Why? Because at the netlist level, you already did logic optimizations. If you already did logic optimizations, those constants, one of the most powerful logic optimizations is constant propagation. If you do constant propagation, you obtain a design that is simplified, okay? But what happens? That your constant cannot be extracted anymore from the circuit. It's there, okay? Because that's what you use to simplify the system. Yes?
But it would be even harder at this point to get it from there if it's so sparse and the information is so destroyed that how would it be so easy to reverse engineer this constant data?
I don't care to reverse the constant. I just want to copy the chip. Right? If I copy the chip as it is, I copy the GDS too. Right? I don't care whatever it is. Okay? Different problem is that if you hide that information and you have to reverse engineering the chip in a way that you need to understand what is inside because you may have alternatives. Okay? So if you write the instruction level to the FTL or to the level synthesis, you have more semantic information that you can protect, okay, and also more impact. So the concept of logic and then behavioral locking is quite simple, even if it is very difficult to be achieved. Is that you want to hide the circuit functionality, making it dependent on an external input, so on a key. So how can you do that? You take your initial design, you make it dependent on the key. Okay? So imagine that you have just one simple operation, an addition. And at that point, those two inputs go into an adder and a multiplier. And the output is multiplexed by 1 key bit. So basically, based on the value of the key bit, your circuit could be an adder or a multiplier. Okay? So it means that given a key bit value, you can create 2 to the power of k possible alternative netlists. And if all these netlists are, let me say, equally valid, it means that they are all possible alternatives. And the attacker doesn't know anything about that. And then only the final designer can apply the key. This type of locking can be done efficiently during HLS or directly on the RTL. Okay? During HLS is nice because you can do more optimizations and so on. During RTL is interesting because you can take whatever input you want, any HLS tool, any pre-existing AP or manual design, and apply it to behavioral as a post-processing. So you obtain something that is secured and you obtain the netlist. It's something that looks simple, right? But it's something that companies don't have at the moment. Okay. So for example, the tool that we designed has been integrated into the robust design flow that is a collection of tools to design circuits that is being released by the IEEE CEDA. So these three, this logic blocking, either the HLS or the RTL version are based on the concept that you may want to obfuscate. You want to obfuscate semantically the semantics of your circuit. So it could be the constant that you simply take out from your circuit and you make it independent. You make it directly connected to the input. The operation is with the multiplexer that I mentioned before, and the branches, the test of the branching is instead of obfuscating with XOR. The XOR is the operation that is used because it is reversible. Okay? If you use the key to encrypt and to generate the value, then you can use the same key to again get the correct value. So once you have this, I conclude with a brief introduction to FPGA reduction. Is the use of the concept of FPGA as a security feature. Why? Because what is the concept of FPGA? That you have a programmable device that when it's fabricated, so that is programmed after it's been fabricated. When it is fabricated, it's exactly fabricated with the concept that the user can use it for whatever he or she wants, but simply implementing the functionality. How can we use it as a security feature? Simply by putting the module that you don't want the foundry to reverse engineer onto the embedded FPGA. So you create an embedded FPGA. So when the chip is sent to the foundry, it simply sees in an embedded FPGA. So it means that whatever in that part, you could have whatever functionality you may have with a certain number of input outputs. Okay? So the idea is that you need to reorganize completely your EDA project, because now you have to introduce new modules, these FPGA netlist. So you have to create the custom FPGA instances, and the protection is given by the protection of the bitstream. If you are not able to reverse engineer the bitstream, or you are not able to understand it from the circuit viewpoint, you are not able to understand, to reverse engineer the functionality. So the reorganization means that you have your original design. Maybe you want to replace this IP with an embedded FPGA. So you can replace the entire FPGA, so the entire IP with an embedded FPGA. You have the best security because you redacted the entire module, but obviously the worst overhead because you have replaced an entire IP. But maybe at a certain point you realize that your IP is composed of modules that are in part the core business, but in part are not so important to be protected. Imagine the accelerator that we discussed before. You have the read, compute, and write. What are you interested to protect? The computational part, because that's the real algorithm. The rest is data transfer, is most likely DMA engine that is most likely public. Okay, so you may decide to protect only one module out of these, one submodule out of this. Maybe the security is bad because now it's really limited, but you have the best overhead because you really protected the minimal part. Okay? And then you can go to any trade-off. So maybe you protect two modules and then you balance security and overhead. When you talk about security, what is influencing the security is especially the characteristics of your embedded FPGA. So for example, the configuration, the parameters, how the embedded FPGA is used. Okay. So what we did last year, not this year, 2020, we published this at DAP 2022, was the identification, was a flow that was able to do this automatic EDA project reorganization. So we started by identifying the possible modules that could be extracted from the design. We try to cluster them because at a certain point we realized that it was not so helpful to have very little time in the embedded FPGA, but maybe two modules could stay into the same embedded FPGA. And then once we cluster these, we characterize the corresponding embedded FPGA, and we offer them to the designer. And we were able to combine the embedded FPGA netlist with the top ASIC models. Okay, and it was interesting because our flow was able to respect the number of instances that the designer wanted, was able to maximize the IOB and CLB utilization. That was one of the factors for security, and there was no overlapping among the module instances, because obviously when you redact a module, you want that is reducting only one element, because also then you have to reconnect your design. And actually, this result was also interesting to see that here, because here, for example, we show two designs of the same benchmark, where we use one 5x5 embedded FPGA and two 4x4 embedded FPGA. And if you see, it is quite surprising, but the two designs were almost identical in terms of a final area, because of how the FPGA were generated. Which design is best? Again, it depends on how you want to evaluate that, because two smaller embedded FPGAs, in a certain sense, it looks counterintuitive, but are more secure than one larger. Why? Because if you break these, you already have recovered the entire design. Here, you have to break two problems. Okay? So it's kind of exponential, because one is depending on the other. So we have automatic system level organization, okay, of the FPGA instances and the rest of the design. The framework complexity was low, okay, only few minutes to evaluate hundreds of alternatives for reduction, and you were able to identify different possible partitions based on your constraints. Then the designer can decide what to do. Okay, and for example, you can use a smaller FPGAs or bigger ones, and then it's left by the design. Okay, and that was really nice, because it's an idea that was really well received by Jack. So for me, it was particularly nice to be presented, because when we presented this paper, you know why we called it Alice? Maybe Lana knows that.
Because it's your daughter.
It's the name of my first daughter, okay? And so I decided to have a paper for her at that. And it was really funny, because it was presented the week after I had my second daughter, okay? And so when we presented the paper, we promised that we're gonna come back with a paper also for the second one. Okay? So in conclusion, the accelerators are becoming key components in modern architecture. So you cannot imagine now an architecture without accelerators. You need data management techniques that are becoming even more important than the pure kernel optimization. This nice HBM architecture, this high bandwidth memory architecture, can offer high bandwidth. That's why they are called high bandwidth memory architecture. But designing for For this type of architecture, it's not so simple. Okay. Also because then you have a lot of, I mean, the exciting says, oh, you can reach up to 460 gigabit of data per gigabit per second, but it's completely ideal. It's on paper. Then you have routing issues. Then you have whatever you want, because yes, you can bring 460 gigabit of data on the board, but then you have to do something with that. Okay? Then to address the increasing complexity of this design, you need something to automate the design, okay, to automate at least the hardware generation. Maybe you don't, it doesn't replace, high-level synthesis doesn't replace the designer, but at least helps to design, to explore alternatives, okay, both for the kernel, but also for the memory. And also we can reuse this design for multiple platform. And this is the work that we are doing in Everest, and especially with the Memozyme and Olympus tool that we discussed. And then once you have design, you want to protect the intellectual property of your design, and with semantically meaningful protection when you are addressing these the chip production, okay? And this is the work in particular that we are doing with NYU, with the Center for Cybersecurity, and these represent the DAO and Assure tools, and then the Alice tool. Okay? Okay, so this is the end of my presentation. First, I would like to thank, obviously, as we always have to do, the sponsors for the research, but also the legal helper, and especially my students that are here, that the part of the work that is this research. So, any question? It's a way to count yeah. Yeah.
One question. So when there is a click, what actually happens to memory? So there are two different numbers, right? That can get clicked. If I go
two different arrays.
Two different arrays that get clicked. So basically, they share the actual physical memory. Okay, and how maybe how do you prevent possible collision? So you ensure that only one part. Like how do
collisions in the sense of the fact that you may have access to one or the other.
Yes.
That's exactly the definition of compatibility. So if you have a compatibility and you identify the compatibility, it means that at the compiler level you have proved that there are no conditions in which you may have conflicts. Right? For example, in the case, let me go back. It's easier in this way. If you see here, for example, once you want to store the array that goes from T0 to T1, you see that is used since the beginning of the computation of T0, because T0 has to write to the end of T1. But for example, this is completely compatible with this array, right? Because there will be no occasion in the same kernel execution in which this data and this data will be allowed at the same time. Right? Could be in different iterations, but that's a different story. Right? So once you can guarantee this, you will never have a conflict. And at that point, this is a guarantee that allows you to completely share and assume that it will work.
And to reduce the area by.
Yes, because indeed, at this point, the designer can have the freedom to do whatever he or she wants with the arrays, even declare a different array for each of the parts. Then is the compiler that identifies precisely the compatibilities, and then is the sharing that says, okay, this is the best configuration to save memory. And for example, in the case of the Helmholtz, we had these 6 temporary arrays that we were able to reduce to 2 or 3. Yes. So we were able to reduce at least a temporary by, yes, because at least the idea is that you can use 1 here, 1 here, but here you reduce this, and so on.
Yes. And for example, just maybe a stupid question. It wouldn't be in this way easier doing malicious attacks, for example, trying to access one, trying to overwrite one side, if they share the same memory bank, to try to access one array with the other? No?
In the case of address space compatibility, there is no concept of one in the other, because it means that the other doesn't even exist. It's not even alive right now. Right? Could be different for the memory interface compatibility, because in that case,
if the portion of the program that wrote to the memory in the first place, and then that portion, the array is dead now. Now on the second portion, using that same memory space, if it does a read first,
but that
then
means
it's
that
reading
the code is incorrect.
Still,
Oh,
if
yeah.
you want to access it,
Okay. So you need something malicious that reads before. Yes.
so you can have another FPGA that you change, for example, and then access to the same memory.
Yeah, that would be more difficult, because it means that you may need a second FPGA that is physically, but also then has a physical connection to those memories, right? But then, I mean, the only effect is that if you can tamper the single kernel, that one of these T0, T1, and T in a way that you may want to read the data before and read them out. So in case now you are in your work. Okay.
Kind of curious how you're using cloud FPGA for this application.
That's my idea. At the moment, we are trying to still to design the interfaces and so on. So at the moment, the idea is to try, correct me if I'm wrong, I mean, here you have 7 loops, no? And try to use a cloud FPGA instance for each of the loops, each of the stage, right? Maybe execute multiple times, possibly in parallel, and then connect them in a kind of chain to bring the data back, right? But we are still in the debugging phase.
Okay.
That's why he's here, because tomorrow we will be right behind to debug. Yeah, but I mean, there are two different problems. One is how to target cloud FPGA, and that is conceptually easy, in the sense that the same flow that you may have here. Can be used identical also for cloud FPGA, because you have the platform libraries in the host, will be maybe not in C++, but it depends on the specifics. But then the system will be not the same size, but will be most the role of the cloud FPGA. But the idea is that the backend also here, this backend is divided into the platform independent and platform specific backend in a way that you can then design the files. So this is more the automation part. Then the efficiency part is something that is, I don't want to say at the moment beyond the scope, but at the moment we are more focused on understand how to create alternatives. Once you have alternatives, then we can understand, we can evaluate, we can design alternatives, we can try, and so on. Well, one possible alternative, as I said, one possible design is, as I said, for the almods is try to divide by stage. If you have that to suggest.
Did you try like just this algorithm, or there like other algorithms as well in the application that you try?
At the moment, we are using this algorithm as a kind of baseline, not baseline because we are not comparing to this, okay? But since we know that well, we are using that to create the complete flow. Once we have the complete flow for this, we may want to address the others. Also because, for example, for the weather simulation, we realize that it's extremely similar to these almods applications. So it will be maybe different tensors, operations, and so on. But conceptually, once we have the complete flow for the almods, it will be simply to change the input DSL.
So there are a lot of similarities between the applications.
At least the first two, because especially because actually, as I said, the first two are exactly based on the same kernel. The third is another. Indeed, we plan to use more cloud FPGA because we have more smaller kernel instances. But in that case, we plan not to use ESL. We are using directly C++ for the PTDR.
It's whatever machine learning thing there. We had a discussion about it, that it might spit out HLSC or it might spit out Verilog. But it's still the front end is.
Yeah, this application is a bit different. It's not, I don't want to say more irregular, but it's more maybe more fine grained. It's not really an high performance HPC application.
Okay. I was trying to understand if you're trying to target some sort of like domain specific accelerator, or it's like really specific for like certain kernel, or because I assume there are like multiple kernel inside each application, right? So if you have like just an accelerator for one kernel, so would you make like multiple accelerators for all the kernels, or there would be like one domain specific accelerator which is able to work with like multiple of these?
No, the idea is really to go towards specialization rather than domain specific, because the idea is that we want to specialize the design for that specific case, even for the specific data set or data profile, with the idea of the variance, because we said, okay, we simply want to reconfigure the FPGA, and especially if you have computation that take hours, even if you spend a few milliseconds or even 1 second or 2 seconds to refresh the FPGA, who cares?
Makes sense.
Yes.
I guess we can thank Christian then. It was a really great presentation, and actually this topic I've been working for a while as well, like on FPGA acceleration. I was focusing on the weather prediction, so I know it's really interesting problem itself, and the project is quite big itself. So I can imagine there's like this, the way you started with like one accelerator makes sense, and it's quite a complex problem, and they're trying to tackle a lot of stuff in the average project, like going from the tool flow and certain accelerators, and also the protection. mechanism. So it's really interesting itself, the complete project. So I wish good luck to you. And thank you very much for the presentation. So, thanks.